Okay, so we have the gradient. Right here, find for a function of two variables, and just as well, we can define as many variables as we like. It's the next line. The number of notation that is used for this is I got 4. So let me erase this. So f prime of let's go high dimensional. So f prime of say a. Okay. So grad a f of a. Okay. And then so f prime like in calculus 1. Grad the del, the Nablith symbol. This one, very popular. And I think I could even use this, df dx of a. Okay, so I got 4. So these two are the most popular in the more advanced mathematics literature, as well as physics or engineering, especially this upside down delta. So we got to use all of them so that you can read whenever it happens. On the other hand, the other two are those are the ones that take you back to calculus 1. So it is Lagrange notation and Leibniz notation right there. Okay, so which one is better? I like it for number 1 because it really makes the point that there is no we're not doing anything entirely new. We're just expanding the same idea of the derivative as the rate of change or changes or rates of changes of a function, no matter what the nature of the function is. But we'll be doing it interchangeably. Okay, and so then these are, if you use f prime, say that will be applicable to, say, parametric curve as well. Okay, so we'll do more of the gradient and all of this theory a bit later. Right now we're up to something more mundane, and that's partial differentiation to begin with, and then optimization and integration. Okay, so partial differentiation, as you can see, so geometry, I remember what was behind, but ultimately it's just applying the same rules as of calculus 1, just in this slightly confusing environment early on, confusing, and then you should be able to just do it as you have always done, and that is just set your mind to first that x being variable, y parameter, and then vice versa, and this is what you see in these examples. Choose constant multiple rule, some rule apply. The chain rule, that's the trouble. That's we cannot do the chain rule in this manner because x and y will be interacting with each other, and that is requires pretty much invoking the whole gradient. Okay, so the function f is composed with another function, possible parametric curve, and then we will need the whole gradient to compute the derivative of the composition. But as far as the partial differentiation is concerned, without compositions of literal compositions, then we were okay applying the same rules, including the chain rule. Okay, so before we apply this to optimization problems, let me do the numerical thing and show you how we differentiate numerically, and just as we did with dimension 1, a function of one variable. Okay, so let me zoom out. Zoom in. Okay, so what is this function? It is a familiar hyperbolic paraboloid, slightly rotated, I think. And let's see. So this is you can see the function here. So it's pretty much, what is it? The red is y squared minus x squared plus xy. That's what it is. That's what it reads there. So it produces once again a hyperbolic paraboloid. And then you can see on right you see these cuts, the cuts along the x-axis. along the x-axis. So y equals b over there. What it means is that we fix the value of y, and then we cut like this. So like this. Okay, and then when we do partial differentiation, we differentiate exactly these curves. So each of these curves, let me show you once again. This is, yeah, okay. So y is fixed. Y is the horizontal axis. So the value of y is fixed over there at -2.0, and the values of x are here. The values of z, these are the values of z, are showed, also used to plot one single curve. So every single curve on the right is made of inputs, same inputs x-axis, and the y and the z's are varied. So for example, here's another one. Okay, you can see that the value of y is fixed at -1.0. Okay, so these are the curves, and these are the ones that we differentiate. But simultaneously, if we do it algebraically, we can do it simultaneously because the presence of y is taken care of. Just the way we did it over here, it's already there, right? So over here we're differentiating with respect to x, and y is already there. So we are getting as if we differentiate into many of those cuts along the x-axis, along the y-axis. Okay, so here. Okay, so let's do it numerically. So what do we do? Here's how we are going vertically, as you can see. So x's are changing vertically. So to differentiate with respect to x, I'm writing difference quotients for x. This is the expression, very simple. Okay, so the difference of the blue one is the current value, red one is the previous value of x, and divided by the h, the delta x, which is at the top over there. Okay, and it is done for every fixed value of y. So once again, I'm creating a new table over here on right. Okay, and I do it according to the formula that I just showed. Okay, and that's exactly looking at this formula. It is computed. As you can see, I will have fewer rows. I have fewer rows. This row is missing because I'm doing subtraction, and then there will be, so if say 20 equals, I have 21 points, but only 20 equals, and therefore only 20 values of the difference quotient. And then I plot it. So I take these, each of them differentiate numerically, and I plot them. This is the result is on the right. Okay, it just happens to be, they happen to be straight lines. Why do you think they're straight lines?
Because they're the derivatives of parabolas.
The derivative of quadratic function is a linear function, so there you go. But not only that, we know that you can make out of straight lines, you can make all kinds of complicated curves. But you can see how these curves, these are the same kind of curves as these, but now we use them to reassemble the graph of the partial derivative with respect to x, which is just another function of two variables. So we start with a function of two variables right here. We slice it this way, okay? Each of them is a function of one variable differentiated. We produce a new function, which is the derivative, and then those functions are combined into a new surface. You can notice that because of the difference, rather the step between each of these straight lines is the same, they do reassemble not only into something, they reassemble into a plane. So, as you can see, it works out nicely in the sense that not only in dimension 1 the derivative of a quadratic function is linear, but also in dimension 2 the derivative of a quadratic function is linear. Okay, so once again, this is the formula of the function is this, and it is of second order. So x appears as second order, y appears as second order, and there's extra term xy also second order. So when you differentiate something like that, you can see that either x or y appear quadratically. Okay, so which means that when you differentiate, you're going to end up with a straight line, and when taken together, in fact, they produce a plane. Okay, so that's what you see here. I certainly could have made an example more complicated, but it is a good thing to see that some patterns still work. The derivative of a quadratic function will be a linear function. So as now I'm doing the same for the y-axis, And so this is, if I go down, this is x is fixed, which my y is now the variable. Okay, so these are the curves as I cut them like this. My surface I cut like that. These are my surfaces. Then each of them is, let me show you once again, it is the output is, where's the output? No, this is the cut. You probably don't see it, but over there, the input is the x-axis, y-axis at the top, and over there you see a start of the output, which is this values of z as y progresses, and every single row in that table produces one curve of those slices. Then we just the way we did it with x's, now we differentiate this in the same numerical way, and once again we get a bunch of straight lines, uniformly distributed, they assemble into another plane. Okay, so let me zoom out and show you the whole picture. Okay, so once again, starting with nothing but data based on that formula, so little table of values, it plots into a hyperbolic paraboloid, this saddle point. Okay, then we slice it. We don't use that. That's just for visualization. Then we slice it. Get those curves, differentiate them numerically with the difference quotient, get new bunch of curves, okay, and those bunch, well, not really bunch of curves, as we are getting that new table over there. So that's one function, that table over here, and we produce a new function over there, which just happens to be a plane. And similarly, we do differentiation with respect to y, and once again we get a new table of values, which is plotted as a plane, and these are its cuts. Okay, so that is numerical differentiation for you. It can totally be done in the same manner as a one-dimensional situation. Okay, questions about this? Okay, so partial differentiation, so it will continue to appear on the in the homework, and we're gonna next apply it to optimization problems. So just like in calculus 1, not in calculus 2, you look at the derivatives, and you can tell, and then you use it. You can tell where the extreme points might lie. Okay, so let's try to review calculus 1, that part of calculus 1, as well as, and then we develop it into the next step, into a multi-dimensional situation. So optimization. So find max min. That's all. That's what optimization is. Functions. Not just all functions. We were unable to, not that we wanted to, but the optimization of parametric curve doesn't really make sense. So we're talking about functions of real values. So parametric curves are vector valued or location valued functions. So you can only do optimization is in terms of, say, maybe magnitude of a distance or something like that. But here we have real value functions, even though the input might be, so that's the output. The input is a vector. So vector, so value of the output is the real number, and the input is a vector. So dimension 1 in calculus 1. So let's quickly review and rebuild the theory. So it's very easy to make a picture of what we are after. So you have your graph. You have a function of one variable, and then you're supposed to find all maximum minimum points. And ultimately, we are after this one as the maximum, and after this one as the minimum. Okay, so that's the ultimate goal. But we first have to describe what it means. That is easy. So say this is C and this is D, and so what we say here that on the interval AB, so f of C is a global max if f of c is larger than f of x for all larger than or equal to for all x in AB. Okay, and D is a global or absolute, if you prefer, minimum if f of D is less than or equal to f of x for all x in AB. Okay, before going into any complex, more complex notions of optimization, let's just right away take these two ideas and generalize into the multidimensional case. What's the trouble? No trouble really. So we are talking about a function that is typically, that doesn't have to. We already have seen the functions with the various domains. So, but it is a typical situation when the domain is a rectangle, okay, on the xy plane, x and y, and say this is on x-axis it's from A to B, and the y-axis from C to D. I think I'm running out of letters. Okay, so hold on a second. Let me think of different letters. You don't want to repeat the letters. Okay. P and Q. P and Q. So this is maximus P and minimus Q. But the interval is AB. And now we are in a similar situation, and we're trying to maximize the function over, which is defined over this region, which is often a rectangle. Might look like this. Okay, so that is my surface. Okay, but the algebraic representation is exactly the same, except the typically we would rather capitalize things to indicate that we're talking about a point in the say x capital in the xy plane. Okay, and then the interval is is rectangle, which is now it is AB cross CD. Okay, so it's the values of x, the first interval, the values of y, the second interval, and that's the rectangle is the domain. We could assume easily that there is nothing else. The function is undefined everywhere else. It simply does not exist. Okay, so and then the issues are exactly the same, and in fact they are expressed in the exact same manner through inequalities. So we could just take these two sentences and rewrite them with the same words, but just need a new type of function. Okay, so let me do that quickly. So P capital is a global max if f of P is larger than or equal to f of x for all x in R. Let's say this my R is my rectangle. That green rectangle is where my function resides, the inputs reside. Okay, and then I do the same for the other one, global minimum. The inequality is the opposite. So the idea is also the same. It's like talking about terrain. Terrain as if it is we have a side view of a terrain. This is the terrain, right? Or we have a terrain that actually is two-dimensional, so we're looking from above. And then furthermore, once we're moving on to higher dimensions, this is the advantage of this definition. And our multidimensional notation is advantageous because that R doesn't have to be a rectangle. It could be, to begin with, it could be any set in the plane. It could be, for example, a circle or anything you can imagine, a star. Okay, and then you move on to the next dimension, and the typical domain for a function in dimension 3 will be a box. So in 3 dimensions, the function would be defined on something like this. Okay. So but the algebra doesn't change. So these definitions will stay with us. Okay. So now we know what we're after. So once again, just as here we saw highest point, lowest point. So this might be the highest point, and that is our P here somewhere. And then we have lowest point maybe this, and that might be our point Q. Okay? So just it just happens the function have more than one variable. It is very common. So what to do with it is fairly simple. We will go with the first derivative test. First derivative test from calculus 1. So we're not going to do the we could, but we probably won't the second derivative test. So the first derivative test. Well, actually, before that, let's make one very hopefully obvious observation: is the relation between these two problems and the discussion that we have had. The maximum minimum points versus of a function of two variables versus maximum minimum points of a function of one variable. How do we get from one to the from the latter to the former? Like this. And the answer is just the way we did just a minute ago. We fix one of the variables, and instantly you have a maximum point. Okay, you have a function of one variable, and then all the techniques that we're going to use, such as the first derivative test, will be applicable. So the idea is then, as I said, fix, say, x equal a or y equal b, and then now what's good is if our point here t is a maximum point, it is a maximum point with respect to those two variables. Okay, so let me make it clear. So like this. So these are our two functions, the variable functions, if you like. So our surface is kind of a cut here. Okay, and this is our maximum point. Okay, so the function is z equal to f of xy. This point is AB. Okay, so now what we do is we create new function z equal to f of xb. It is this one. Okay, z of xb. If we cross it along the x-axis, so the variable is x. Okay, and the other one, we cross it this way along the y-axis, and this graph is equal to f of ay. Once again, function of one variable. Okay, so that we already have done previously, and now the point is that now if AB is a maximum value, a maximum point of the function of two variables is equal to xy, then it is also a max for both of those two functions. Z equal to, once again, f of xb and z equal f of ay. Okay? Just looking at the picture, it's certainly no trouble. The point is that it's the highest point. So if the highest point from a helicopter, then it will be highest point if you start walking around either north-south or east-west, it will be the highest point. So in fact, if anything, that this kind of a transition ignores the possibilities that there's something happens in the diagonal direction. But remember, once again, we are going for the first derivative test, which goes only one way. It gives you a necessary condition, but not sufficient condition of extreme value. So that's what I'm about to do. So f is differentiable. So once again, we go to function of one variable, and differentiable at x equal a. Okay, then I really run out of letters. Okay, so I'll just have it separated like here. And so different letters mean different things. Okay, so differentiable at x equal a, and x equal a is an extreme point. then f prime of a is equal to 0. That's the first derivative test. Once again, goes only one way. If then, you cannot go backwards. Derivative equal to 0 does not mean that it is a maximum or minimum point. The counterexample is the cube, and then the advantage, the point of this theorem is to come up with a list of candidates for extreme points. That's how it worked in calculus 1. So that's why it's okay. It's okay to abandon the possibility that something nasty is happening in the diagonal directions. That's okay. We're still just trying to reduce the number of candidates as much as we can, and we are doing it with only the two partial derivatives. Period. Okay. So let's apply it to this is local. Okay, so apply to these two formulas. Let's apply first to z equal f of a y. Okay, it is defined on a well, doesn't matter where at this time. Okay, so what we have here is then if AB is a extreme point, then df df no, I meant the other one. Sorry, I meant here dxb first in that order. df dx at AB is equal to 0. Okay, so that's exactly what we're talking about. It's the same function. I mean, if you were concerned about this using the same letter, how about I put a g here so we wouldn't have to worry about it. So we have a function of g, which is simply the original function of two variables f of x, y, with one of the variables this time y fixed at b, and then once again this picture that I will keep referring to. This picture we are looking at one at a time, and then all we want to do is to come up with a condition for that every extreme point has satisfied, and the condition is right here. Okay, but that's one. That would not cut the number of candidates significantly significantly enough, as significantly as if we have two conditions, because these have to be satisfied simultaneously. So I'm taking this f of ay, and once again, if this condition is the same, if AB is an extreme point, then df dy AB is equal to 0. Okay, so once again, that's the key thing, is that the condition of the precondition for this is the same. So the condition for our conclusions are different, but the condition is the same. So if it is extreme point as a function of two variables, the highest point, whether you go this way or that way, and either you go this way or that way, you have the derivative equal to 0 of that one with respect to x, and then with respect to y. So you have two conditions rather than one. Okay, and that certainly cuts the. So you have two equations. You probably need two because after all we have each of these will be a function of two variables, and what you were talking about is just like in calculus 1, you have one variable, one equation, and they'll give you generically just a few answers, and that was good because that was just a list. And here you have two variables with one equation, you probably will have infinitely many answers. But if you have two equations, well, then things work out. So let me, it's really straightforward, so I'm going straight to an application. So once again, a quadratic function. Okay, so once again, we need to maximize the function. We certainly already know enough about this function to know what it looks like. What do you think it looks like?
It's another hyperbolic parabola.
No, actually no. That little minus here that over here, what creates a behavior that is this way. That minus creates, when you have two plus, it means that with respect to x and y, both of the parabolas branch up. Okay, so fix x, I'm left with x squared. The leading term is x squared, so it branches up. If I go with y, once again, the leading term is positive, so it branches up. So the whole thing creates this cup, which is called the name of it is, we've seen it, but I don't think I named it. It is called the elliptic parabola. Okay, want to guess why elliptic?
Because cross sections are ellipses.
What do you mean cross sections?
Oh. If we cut it with the plane parallel to one of the axes.
No, that is the paraboloid part.
Oh.
We can't cut vertical, we get parabolas, just like with the hyperbolic paraboloid. Hyperbolas come from cutting horizontally, just as these ellipses will come from cutting horizontally. So once again, it looks like this, and if we're cutting it horizontally, then we'll get a bunch of ellipses. When we're getting a bunch of hyperbolas, we get a hyperbolic parabola. But we ignore that, this inside, we are trying to verify this idea, and but we do know that there will be probably one answer. Okay, so it's good to know ahead of time that we are probably okay. So I am doing partial derivatives. So is 2x plus 1. Okay. df dy. What's df dy?
4y plus x.
4y plus x, yes. Okay, so these are the partial derivatives. We don't really have to think in terms of the gradient. I mean, all we have to do is those two equations to be solved. So indeed, I set these equal to 0 and solve just like in calculus 1, except once again, instead of having one equation, one variable, we have two equations, two variables. So a little bit more work, but it gives pretty much works out exactly the same way. So I say I take maybe the last equation. From the last equation, I have x equal negative 4y. Substitute into the first equation. So what do I have? 2 negative 4y plus y is equal to 0. Okay. And or negative 8y. Or negative 7y is equal to 0, so y is equal to 0. Okay. Y is equal to 0, and then, so back substitute, and so y is equal to, also, x is equal to 0 as well. Okay, so maybe not entirely obvious it was from the beginning, but the symmetry is revealed that indeed that the ellipse that if we're looking from above, we see those ellipses. That ellipse is centered at 0, as a matter of fact. What would it? Well, the y is not. Well, what would shift the ellipse away from the origin would be terms such as x or y alone. So as you can see, all of the terms here are quadratic except for 7, x squared, y squared, xy, also all quadratic terms, and that's why there is no shifts horizontally on the xy plane of what we got, and we have the symmetry around 0. Okay, so that's good, but once again, if we pretend that we don't know whether or not this is a minimum or maximum, so all we know that this is a candidate. This is a candidate for an extreme point. We do not know that for sure that it is, and if it is, whether it's one or the other. Okay, so one way to do it is a sampling. Unfortunately, that creates an infinite many possibilities, but certainly that is a valid way of doing it, because after all, f of 0, 0, that point will be 7. And if, on the other hand, what I can tell I don't want to sample one at a time, so I could, I would like to look at the limit. F of x, y, what kind of limit would be relevant here?
I mean, couldn't we imagine, if we cut the figure with the plane through
Yeah.
to point 0, 0, and then we look at what the cross-section does?
Right, but that would be only give you one. You add one, another variable, it's also one. You actually would have to end up with cutting with every single plane and hope that there is no some direction in which you are not, the function, the point is to compare this, to show that 7 is the lowest value. So I certainly could pick a bunch of values, plug them into the function, say 1 plus, if it is 1, 1, I will end up with, 11. So f of 1, 1 is 11, which is good, so it's larger than 7, but I don't want to verify all the many points. So so I want to understand the general picture, generally what the graph looks like. Look at it, we know what it is, so we can actually guess what we should look for. And I say there is a certain limit that we can look at. The limit? It grows. So in fact, xy go to infinity as what?
That's the magnitude of x and y goes to infinity.
Yeah, that's right. So the distance to the origin is going to infinity. So as we progress away from the origin, no matter in what manner, not straight line necessarily, you can go spiral or wherever you like on the xy plane, as long as you're getting farther and farther away from the origin, what's going to happen to the function? It will be going to infinity. So that's certainly true, even though you probably would have to actually prove that. And it gives you an idea of what the graph roughly looks like, and that indeed it proves that once done that this is a minimum point. Okay, so this is a minimum point. Another way to specify, to figure out what kind of extreme point it is from calculus 1 was what? Classify extreme points. What? Second derivative. So the other option is the second derivative, and it is done in the exactly same manner. It is we'll just compute the second derivative. So for example, so we're still sticking to two directions. So it will be still how should I say? It's still sufficient, no, necessary, but not sufficient condition. Great. That thing flew. Tip of the pen. Okay, still right. Okay. So second derivative. The second derivative is then with respect to the same variable. So I will be doing ddx of df dx, okay, just to find out what the cut looks like. The cut is, I'm cutting like this along the x-axis, and we're certainly going to discover that the result is another the parabola. Okay, to confirm that if it's not a parabola, what can we do with it? And what we do is we just differentiate. Look at the sign of the second derivative. Okay, so we differentiate with respect to x function to x plus y, and the answer is 2. So it's positive, concave, up. So that slice, that green slice over there is concave up. That's all we can tell. We don't really have anything else, anything better. And then I do the same with the variable of y. It is once again not really the second derivative test. The problem that the second derivative test is not going to really work here is, what is the derivative here for y plus x? So once again, the first derivative test gives you necessary but not sufficient condition. Necessary for extreme point, the derivative has to be equal to 0. The second derivative test in calculus 1 gives you a partially converse. So if the derivative is equal to 0, and the second derivative is positive, then we have a minimum. Okay, so just like this. First derivative 0, second derivative positive, concave up, it is a minimum point. So converse. Unfortunately, we don't have this luxury, so I can concave up. So the other one is looking like this. Like this. So the other look, if I'm cutting my plane, now I'm cutting along this one, so I'm ending up with something like this. Another parabola, and now I discover that in that point of interest at the bottom, it is concave up. Okay, so together, however, we realize that this is not enough for us to make the conclusions that we want to make, which is it's a maximum, or I'm sorry, minimum. And unfortunately, no. So it's still because by doing it this way, we ignore all the possible diagonal directions and some nested things that possibly can happen there. So we cannot assume it. So we know so much about this function, so we know that nothing is happening. But in general, it is possible that you can have a settle point. Well, there might be. Well, let me take a look at. Well, actually, this one was pretty good before I erased it, but so you could have a bunch of parabolas in one direction and the other direction, but there is still diagonal direction. You can have it is conceivably you have a parabola hanging down. Okay. So anyway, we don't have enough information here. So the second derivative test for two-dimensional second derivative test so it works for dimension 1. So once again, f prime of a is equal to 0, and with differentiability, a is positive. The end is a minimum. Okay, so that's how the second derivative test works in calculus 1. And now it fails because it's only, once again, we're only able to eliminate some other candidates. So imagine that we did this computation when we ended up with one number positive, the other negative. Okay, then we would know that, what we would know? We would know that it is not a minimum, right? So it's a way to eliminate some of the candidates. So even though the both of them are equal to 0, so it creates kind of a cross once again, and in fact you realize that the tangent plane is horizontal, but looking at the second derivative will help you to eliminate some of the possibilities, some of the candidates for maximum points. Specifically, so let me quickly, so dimension 2 later, but second derivative test. That works only one way. We could quickly apply to xy, so f of xy is equal to xy. Okay, so the one that the hyperbolic paraboloid, df dx is, well, maybe it's not a good, how about plus x minus y. Okay, let me try this one. Okay, df dx is y plus 1, df dy is x minus 1. So if I set these equal to 0, I'll have y equal to -1 and x equal, so this just creates a shift. What I was looking for is the settle point. The trouble with xy, unfortunately, why that example doesn't work out, is that okay. Well, let's do it anyway. Let's see what. So xy, there's with respect to x is y. If we both set it equal to 0, then there will be 0 and 0. So y is equal to 0, x is equal to 0. So candidate is the only one is 0, 0. Okay, and then if we want to verify it with the second derivative, that's where things kind of fall apart, the way I tried to do in the previous example, and that worked out. So the test, we passed the test. So that's what happened here is that we passed the test in the sense that the signs are the same, and it is possible that that point is a minimum, but it does not. And this is an example of when the test fails. It just failed. Okay, so I'm doing the second derivative with respect to x, same variable, so dx of df dx, which is ddx of y, and it is equal to 0. Okay, so what does it say? It has no concavity, right? So at 0, what's the term when the second dy of x also equal to 0, and so once again the test, it doesn't fail the test fails. Test fails. Okay, test fails means that it doesn't mean that it is passed it. It doesn't mean that it violated it. Well, the test fails because it only applicable when either one or the second derivative either positive or negative. Okay, since both of them are 0, well, it is inconclusive. But other than that, this is roughly how it works, and we have to carefully apply the methods that we know from Calculus 1. The terminology also fully applicable, the same. So you have local minimum maximum points. You also have the local maximum minimum points. You have critical points. So local minimum maximum point is when you take the whole graph of yours and limit your attention to only a small, in this neighborhood or vicinity of the point of that point of interest over here. So you cut the piece of the graph that is maybe like this, and then look for whether or not this is the highest point over here. It might be, and then all you need to do this is the first derivative. Okay, and what else? Well, I guess it's worthwhile to actually state it that in this form, df a is equal to 0. So this is a necessary condition for the point A to be local extreme. Okay, so we're gonna do a little bit of this next time, and then we'll do integration.